Chapter 17, our last chapter together in our journey of AP Chem, looking at yet additional aspects of equilibria. Thinking about more equilibrium problems, products over reactants. We'll be investigating the idea of common ion effect. You've had a little lesson on that in terms of AP review. The concepts of buffers with Henderson-Hasselbalch, acid-base titrations, which we commonly called solution stoichiometry, and then those factors affecting solubility. So 4 new lessons, a very abbreviated note pack, and we'll begin in the first lesson of the common ion effect. And as we turn our page to that first new note pack, Applying Equilibrium, Chapter 17, we're going to investigate the first section, kind of illustrating what the common ion effect is, and then working some sample problems together, giving you enough ammunition to be successful in homework lesson 1 from Chapter 17. So as we begin, let's think about the common ion effect. When we have 2 solutions, each with an ion that's in common, we'll look at that as the common ion effect. And one of the first examples reads, when we have a salt with an anion of a weak acid, it reverses the dissociation of the acid. And it literally does so by lowering the percent dissociation. Now let me make sense of what this sentence is saying. Let's suppose we have any weak acid. We can let that be represented by HA. The term weak acid is telling us, let's suppose we have an equilibrium where hydrogen ion and that conjugate base called A negative, whatever the last name is for that acid. Now, according to Le Chatelier's principle, if we were to apply a stress, and that stress would be adding an ion that's in common with this last name. Let's suppose I just take a salt called, of course now my pen doesn't work, let me try to find a better one. Let's say a salt, something like Na, and then I have A negative. So sodium A negative. It could be like acetic acid. This would become sodium acetate. Whatever the last name is, it just needs a first name. We need to call that a salt. But the stress would say, if I add to this weak acid equilibrium an ion that's in common with it, such as the last name, acetate, or whatever A negative is standing for, that's a stress. And of course, Le Chatelier says we're going to do the opposite to alleviate that stress. By forcing the equilibrium left, we're taking hydrogen ion out of solution. This then becomes less acidic, and that's the same as saying raising the pH. By adding a salt to the anion of a weak acid, we literally change the pH of our solution by removing hydrogen ion. You know, that same principle applies to salts with this, there's the bell, with a cation in common with a base. Now let's just use some generic chemistry here. Suppose we have a base, and we'll just let that be represented by B, and we place that into a water solution. We set up an equilibrium where conjugate pairs are forming. This would be Kb chemistry, simply because we're producing a hydroxide ion. It's telling us, what if we put in a salt who has the same first name as the base? Ammonium chloride, or thinking of something that's in common. Well, the stress says, well, what if we add more of that same first name? Literally, we force that equilibrium left, and when we do so, we remove the base ion, so it becomes less basic, or literally drops the pH as it becomes more and more acidic. So the common ion effect really is saying we're going to be studying an acid-base equilibrium. We're studying some sort of equilibrium, and then really, according to Le Chatelier, we cause a stress, and the stress is putting something in common with it and watching it shift from left or right, and then recalculating based on an ice chart. So as we consider The approach to solving common ions, it really is thinking about step one, what are those major species in solution? Are we doing Ka chemistry for acids? Are we doing Kb chemistry for bases? What is it that we're actually studying? Get up an ice chart. We know that if we're studying Kas, we want to consider hydrogen ions. They determine pH. If we're studying Kb chemistry, we're going to be determining hydroxide ions because it will determine pH of a solution. And we just simply tabulate the ice chart, knowing that it's the E row that's of interest to a chemist, the E row giving us the equilibrium values when we go to calculate the equilibrium constant. Let's dive in with an example. I'll read it with you and just ask you to follow along. We'd like to know the pH of a solution by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate in enough water to make a 1 liter solution. And Ka is given to us 1.8 times 10 to the negative fifth. Step one, figure out the chemistry. What are the major species? What is it that's involved in this equilibrium? The weak acid is acetic acid. The very definition of weak says it sets up an equilibrium. It will do so by creating ions of hydrogen and acetate. The equilibrium is represented with a Ka value 1.8 times 10 to the negative fifth. But we also have a competing reaction into the same solution. We have sodium acetate. Sodium acetate here's one that works. Now this is a salt, and the very definition of a salt says 100% of it is going to ionize. It's going to give us sodium ions and acetate ions. There's no equilibrium for a strong electrolyte. It 100% dissociates. But there is an equilibrium for the acetic acid. Here's what we know. Sodium acetate, 0.3 moles in 1 liter, that's 0.3 molar. When it dissociates, we get 0.3 molar sodium ions and 0.3 molar acetate ions. Of course, this is the ion we have in common with the equilibrium of the acid. This is the concentration we know to be of the acetate ion. So the 0.3 molar I can carry down knowing that it's already in solution coming from being the conjugate base of our weak acid. We know the initial concentration to be 0.3 molar. This would be 0, 0 plus 0.3. There's the common ion effect. And that's why I'm just carrying down 0.3. As time goes by, the acid gets used, minus X, 0.3 minus X. We'll let hydrogen be X, and technically this should be 0.3 plus X. But here's where the math is made easier, assuming that 5% rule. The plus X and the minus X get tossed out. So in other words, when we are looking at the amount of acetate ion that's being contributed to this equilibrium from the weak acid compared to the amount of acetate ion coming from the salt, it's negligible. It's not worth adding into the math. Ka simply becomes products over reactants, and look what happens. 1.8 times 10 to the negative fifth is the Ka. Hydrogen is X. The common ion between the salt and the weak acid is 0.3 molar. And in this particular example, because we were given equal amounts, this also is 0.3 molar, the concentration of the acid. The math simply shows these canceling out, and X becomes the Ka of our weak acid. Remember, we let X stand for hydrogen ion. Negative log, the value that we found for Ka, and we'll find our pH of the solution. So far I haven't hit my calculator, but when we hit negative log of 1.8 E-5, the Ka value for our acetic acid, our pH comes out to be 4.74 pH units. And does that number make sense? Yeah, it's a weak acid. We need to have that in terms of and in the acid range of our pH scale. So here's what we've done. We consider the important equilibrium. The equilibrium that's going to determine the pH is coming from the weak acid. It had an ion in common with a salt. That salt was called sodium acetate. The concentration of the salt became the acetate concentration in this particular equilibrium. Because the amount of X was so small, we tossed it out and set up a products over reactants where Ka became directly the concentration of hydrogen ion. It was then used to determine the pH of a solution. Let's consider a next example. Let's calculate the pH of a solution containing 0.085 molar nitrous acid, it's Ka provided, and 0.1 molar potassium nitrite. Now think about the competing equilibriums. The weak acid, HNO2, is nitrous acid. Very definition of weak says it's going to set up an equilibrium. And when it does so, we get the two ions, the conjugate acid hydrogen ion, its conjugate base nitrite. It has a Ka value of 4.5 times 10 to the negative fifth. Oh, excuse me, I'll repair that right now, to the negative fourth power. Also in solution, in a separate scenario, we have its salt, potassium nitrite, KNO2. The very definition of a strong electrolyte says it 100% dissociates, so that if I had 0.1 molar potassium nitrite, it's going to form 0.1 molar of potassium and 0.1 molar of nitrite, the strong electrolyte. So therefore, this value, the 0.1 molar, becomes the value, we'll carry over here, 0.1 molar nitrite, the ion it has in common. Now the other thing we'll know is the solution started at 0.85 molar of the acid. And again, in this first example, I set up the ice chart and then described to you how we know to toss out X. We can assume that to be true throughout this entire series of problems. So I'm going to just record underneath that then the 0.085 molar. The value for nitrite, 0.1 molar, and we're going to let the value of hydrogen ion be represented by X. I know technically this should be 0.085 molar minus X, and this should be 0.1 molar plus X. But let's assume that the concentration of nitrite coming from this dissociation of the acid is so small, negligible, it's not worth measuring. The Ka value, 4.5 times 10 to the negative fourth, is equal to the products, hydrogen ion, nitrite ion, set over the concentration of the acid. Solve for X, knowing that X will give us the hydrogen ion, and that X that we solve for there can then be determined, used to determine the pH. So let's hit together. Please hit with me. We have 4.5 E negative 4 times our concentration of the acid, 0.085, divide by 0.1, and we get X, 3.825 times 10 to the negative 4. Negative log that answer, and we should find our pH directly, 3.42 pH units. Again, a number that makes sense for a pH range of an acid. Let's flip over and see what else is on our agenda here. A couple more problems on common ion. How about these, it reads. Calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. Now we've got to go to work thinking HF. This is not a strong acid. Therefore, it sets up an equilibrium. Therefore, it has a Ka value. It doesn't give it to us. We'll have to look it up. But HCl is the other ion mentioned. HCl is one of our 7 strong acids. Therefore, it 100% dissociates. No equilibrium, no Ka value for this particular reaction. Let me quickly look this up while we have our chart nearby. HF is 6.8 times 10 to the negative 4. Alrighty. So here's the story. This guy, HF, sets up an equilibrium in the same container as a strong acid that 100% dissociates. If I place in 0.1 molar HCl, I literally have 0.1 molar of the hydrogen ion and that of chloride. But of course, this is the ion that's in common with the weak acid. We're being asked to calculate the fluoride ion. If it had asked us for pH or of a hydrogen ion, there it is, 0.1. I mean, that's the major species. So tabulating what we know in common. Let me just rewrite our equilibrium since this is what we're considering when we solve for our math. The 0.2 molar was the concentration of HF. The contribution of the hydrogen ion is coming from the strong acid, 0.1 molar. Now, fluoride we can let represent X. We don't know its concentration. Now, technically, this should be 0.1 plus X. This should be 0.2 minus X, but let's assume that X is so small, so negligible in the amount it contributes to the equilibrium that we can simply toss it out. And we can solve for the fluoride ion, calculating X, and we can solve for the pH by knowing hydrogen ion directly. So the Ka I found for us, 6.8 times 10 to the negative 4th, is equal to the hydrogen ion times the fluoride ion over the acid, 0.2 molar. Solving for X, knowing X is giving us the fluoride concentration that we have in our equilibrium. 6.8 E negative 4 times 0.2 divided by 0.1. And we get a value of 0.00136 molar, the concentration of fluoride. And the other part of our question asks for pH, and that's negative log of the concentration of hydrogen ion. So 0.1 becomes the hydrogen ion, and of course this is written as 1 times 10 to the negative 1, so the pH comes out to be 1.00. Remember your 2 decimal place rule. pH of our solution, very strong acid, 0.1 molar, gives us a pH of 1.00. Letting X stand for fluoride, we set up our equilibrium problem and pulled out the fluoride ion. Friends, we'll try one more together, wrapping up our common ion lesson. At the end here, we'll have accomplished enough information to do lesson number 1 off of our assignment sheet. We're going to calculate the formate ion and the pH of a solution that's 0.5 molar in formic acid, provided for us, Ka, and 0.1 molar nitric acid. This sounds very familiar to the previous example. We have a weak acid placed in with a strong acid. Of course, the weak acid sets up an equilibrium. See that COOH? Right there is your ionizable proton. Hydrogen ion and HCOO negative, the Ka 1.8 times 10 to the negative 4. Nitric acid is one of our strong acids, 100% dissociates. The ion that these two equilibriums or these two reactions have in common is the hydrogen ion, the common ion effect. If nitric acid was 0.1 molar, let me get that back on, 0.1 molar, that's the value I carry over to the equilibrium concentration, the ice chart here. We'll let formate be represented by X, and 0.5 molar, the concentration of formic acid. The common ion in this example was the proton, the hydrogen ion. It will be used directly to calculate the pH. Just as above, it looks like right away I can say pH will be negative log of 0.1. pH will be given to us from the strong acid, 1.00. The amount of hydrogen ion that the weak acid contributes in comparison to the strong acid is negligible. Toss it out. And we can solve for our formate ion by setting up an equilibrium problem. 1.8 times 10 to the negative fourth, that was given to us as the Ka. Concentration of hydrogen ion times the concentration of formate, all over the concentration of the original weak acid, 0.5 molar. When we pull out X, we'll have the formate polyatomic ion. Whoops. 1.8 E negative 4, there I got it, times 0.5 divided by 0.1, and our concentration of the formate polyatomic ion, 9.0 times 10 to the negative fourth molar units, the concentration of HCOO negative 1. This ends the lesson on the Moodle site for common ion effect. The next lesson you will be ready for is on buffered solutions, and that will be a different link. You're ready now to start your lesson number 1.